everyone. And first, I'd like to thank the organizers for giving me the opportunity to talk about my recent work on low energy structure of spiral spin liquid. It's work in collaboration with Johannes Reuter from Free University of Berlin. Okay, so the talk has 4 parts. So first, I'll explain why spiral spin liquid is theoretically a very intriguing case. And then I will illustrate the main, say, message or the physical picture. That is, we find a new type of topological defects that play a key role in shaping the low energy physics of spiral spin liquid. And then I'll show some numerical evidences proving this physical picture to be right. And finally, I'll briefly discuss the effective theory of such systems. Okay, so first, let me try to explain why these classical spin liquids are very interesting classical systems. Let's put it in comparison with, say, an Ising ferromagnet. So for the Ising ferromagnet, well, we are all very familiar with it. We know it orders at a low temperature after phase transition, and we know that these systems can generally be described by the Landau paradigm. That is, you identify the symmetries and all the parameters, and you write down the effective theory. And with quantum dynamics, there will be magnons, and these magnons can be described by a band theory. Okay. In contrast, classical spin liquid is very different. Let me use spin ice as an example first. So in this case, you have this interconnected network of tetrahedra, and you have Ising spin halves on this tetrahedra, and the Hamiltonian just tells you that the ground state is that you want 2 spins to point inside and 2 spins to point outside. So you have 2 in, 2 out, which we call this ice rule, which is actually analogous to divergence-free Gauss law. Okay, so for this system, as you can imagine, it has many ground states. Actually, it's extensively degenerate because there are many different ways to arrange your spins to satisfy this ice rule. Okay, so instead of being described by these order parameters, it's often this spin liquids is often described by some classical limit of gauge theory. And now this is the classical limit. And once you introduce some quantum dynamics, then it can become a quantum spin liquid, which is a kind of, or are many different types of topological orders, which are, of course, very interesting. Yeah, just to explain a bit more for the spin ice, why it is a spin liquid is quite well understood. So you have these local loops of spins that you can flip. And by doing this, you will stay in the ground state. Okay, so in the system, there are many of these loops, so you can keep flipping them so the spins never order. And the low energy effective theory is really just described by electrostatics. And of course, if you have break the ice rule, then you have this, say, in this case, electric charges, but in some geo language, it's magnetic monopoles. And in the quantum limit, they become these fractionalized excitations. Okay, now let me explain why a spiral spin liquid is different from this spin ice type of spin liquid, and why there are some unanswered questions regarding them. So the case study example we use is a square lattice model with XY spins with up to third neighbor interactions. Okay, so the phase diagram for this classical model at t = 0 is studied a long time ago. Basically, there are these spiral phases. They correspond to the state that the spins are rotating in the real space corresponding to a particular wave vector. Like here, the wave vectors are these ones in the Brillouin zone. And in this phase, the wave vectors are these points in the Brillouin zone. And so on this thick red line is where something interesting happens. So here you have a sub-extensively degenerate ground state. Okay, so they are not just these points, but instead the wave vector for these ground states form a circle, a ring, like here. And depending on where you are on this red thick line, the concrete shape of the ring can change, but the topology of the ring is always the same. Okay, so it is on this thick red line where these two phases meet that the spiral spin liquid exists. As you can imagine, since this is a very simple model, it has been studied quite a lot numerically. And also people find out that in the quantum limit, this becomes a quantum spin liquid. And experimentally, there are some materials that these people discovered in, say, 2D and also 3D, where people see the signatures of this spiral spin liquid, which is this sub-extensive degenerate ground state, having this, say, forming this sub-manifold in the brilliant zone. Okay, now, so despite all these studies, there is still, say, I think one unanswered questions, which is how can this thing be a spin liquid in the first place? Coming back to spin ice, the picture is very clear because you have this local degeneracies of flipping this loop of spins. Okay, so it's fairly easy to understand how it does not order. However, for the case of spiral spin liquid, you don't have such extensively degenerate ground state. Okay, you only have this sub-extensively degenerate one. In other words, you don't have these local spin flips that takes you to another ground state. Instead, if you go from one momentum or wave vector to the other, that involves, changing all the spins in the system. Okay, so it is not very clear until now, like how could this be a spin liquid if there is no local degeneracy? So what's new here is that this ring of ground state actually gives you an extra U1 symmetry. And so on top of that, of course, you have the U1 spin rotational symmetry. So what we focus here is what's new, this emergent U1 symmetry of momentum rotation can bring us. Okay, so we actually find that that will make a new type of topological defects emerge. So how that happened is that let's consider a small cluster on the lattice, and the spin texture look like this, which correspond to a particular momentum, which correspond to a particular point on this ring. Okay. However, if I zoom out and I look at a much larger piece of the lattice, then I can have this configuration in terms of spin texture. So here, the spin texture is actually continuous. It's not a spin vortex. However, if you look at the momentum, you see that the momentum actually slowly wind and form a winding number 1 vortex. And because the momentum is more or less restricted to stay on this ring, this is actually a stable topological defect because momentum cannot go through 0. Okay. And here is an example of topological number -1 for the momentum vortex. So our intuition is that this new kind of topological defects, which only emerge in the regime of spiral spin liquid, will dominate the system and determine the low energy physics. Yes, and then we go on to do numerics to find out if this is true or not. So this is the phase diagram from high temperature to low temperature, and we find that at high temperature, it's of course just a paramagnet, but as you lower down the temperature slowly, you do enter some regime of what we call pancake liquid. We will not have time to explain that, but then you have the spiral spin liquid phase and the rigid vortex network phase. Okay, so this is very high temperature, and now entering the spiral spin liquid phase. This is a snapshot of the system in real space. And as you can see, you have these co-centered contours of spin configuration, which are the momentum vortices. And then you have these X-shaped objects, which are the anti-vortices. And apparently they fluctuate a lot in the system and lead the system into a liquid state. If you keep lowering down the temperature, one thing we find interesting is that these vortices and anti-vortices actually form some kind of rectangular state, which is a very glassy state. It's not the ground state, but the system is frozen there. Finally, I just want to quickly mention that we do understand what's the effective theory that describes these vortices and anti-vortices. It turns out that they are similar to elasticity, where these vortices and anti-vortices, they are actually similar to adding extra atoms in your lattice or taking away some atoms in your lattice. Another way to understand it is to link it to this so-called rank 2U1 theory. I have no time to explain it, but basically it's new kind of electromagnetism where your electric field is a tensor instead of just a vector. And you have this, say, modified version of Gauss law. And the signature is this four-fold pinch point. It can be seen in numerical simulation. Okay, so basically that's the story I want to tell. So we understand now what's the new topological defects in spiral spin liquid and how it dominates the physics at low temperature. And of course, in the future, we want to look at, for example, the quantum limit generalization to 3D and see if in some experiments we can test our theory directly. Okay, thank you.
Great, thank you very much, Han. Okay, time for one or so two questions. Let me ask a question. Since you have a U1 emergent order, why don't you get a Kosterlitz-Thouless transition in this system?
Good question. So that is because naively you would think, okay, we have the momentum vortices, they probably behave in the same way as the spin vortices, so what's new here? But it turns out that these momentum vortices have very distinct mathematical properties from the spin vortices. The key reason is that if you look at the definition here, then you see that the Q as a vector field must obey some curl-free condition, okay? And this will quite drastically change the mathematical properties of these vortices. For example, the winding number cannot be larger than 1, which is quite surprising. So yeah, so in the end, all these KT physics foundations do not apply to the momentum vortices anymore. So that's the reason why there's no KT physics for the momentum.
What is the nature of the transition? There was a sharp peak in the specific heat.
Yes, we suspect. So we checked this carefully and we don't see any symmetry, discrete symmetry that can be broken there. So we suspect it's just a crossover. And so from high temperature to low temperature, it's always just crossover. And this is just a very, in the end, you just enter a very glassy state that of this rigid vortex network. So here, yeah, it's probably not a phase transition. It's probably just a crossover. And it's just that you need a very large lattice to see that.
Okay. If no more questions, let's thank Han Yan